Good evening to everyone present over here. Requesting you all to put your mobile phones on silent. I am Satvika Samal and it gives me immense pleasure to welcome you all on behalf of Department of Fibres and Textile Processing Technology, ICT-Mumbai, to the second Professor MD Teli Endowment Oration for the year 2024. Shubham karoti kalyanam arogyam dhana sampada Shatru buddhi vinashaya Deepa jyotir namastute. I thus humbly invite our honorable dignitaries to kindly come upon the dais to light the holy lamp and request our head of the department, Professor Ravindra Kale, to escort them. Distinguished speaker of the evening, our esteemed Chancellor, Institute of Chemical Technology, Padma Bhushan Professor J.B. Joshi, Honorable Vice Chancellor, Professor A.B. Pandit, former Head Dean HR, BOG Member, Institute of Chemical Technology, Mumbai, Professor M.D. Teli, Dean HR, Professor Ravindra Adivarikar, Head of the Department of Fibres and Textile Processing Technology, Professor Ravindra Kale, Dr. Armaiti Shukla. I request all the dignitaries to kindly take their seats on the dais. Thank you. We will now have our Vidyapeeth Geet.
संघर्ष नको
I would now request our Honorable Vice Chancellor, Professor A.B. Pandit, to extend our hearty welcome to the speaker, Padma Bhushan Professor J.B. Joshi, with a fragrant basil sapling. Thank you. I would request Professor A.R. Atley to welcome Honorable Vice Chancellor, Professor A.B. Pandit, with a sapling. Thank you, sir. I would request Dr. Kedar Kulkarni to welcome Professor M.D. Teli with a sapling. I would request Dr. Saptarshi Maiti to address Professor Ravindra Adivarika with a sapling. Requesting Dr. Kedar Kulkarni to welcome Professor Ravindra Kale sir with a sapling. Requesting Dr. Sandeep More to present the sapling to Dr. Armaiti Shukla. Thank you, sir. Now I would like to invite Head of the Department of Fibres and Textile Processing Technology, Professor Ravindra Kale, to extend a formal inaugural to today's August gathering.
Honorable Chancellor, Padma Bhushan Professor J.B. Joshi sir, Honorable Vice Chancellor Pandit sir, Honorable Teli sir and his family, Dean HRD of the ICT, Adivarekar sir, RMIT Madam from SVT College, Juhu, my faculty colleagues, students and all the participants, a very warm welcome to all of you. Today's oration is a second installment in honor of our former HOD of the Textile Department, who had also been the Dean HRD earlier in the ICT, our beloved Professor Teli sir. We are fortunate enough to have Padma Bhushan J.B. Joshi sir for today's lecture. Coincidentally, last week only, myself and Kedar sir attended a book release function, the Marathi version of the same, which covered the same topic, that is climate change. And there Joshi sir discussed some points, and I think today he is going to elaborate on the same thing, but in more detail. More information about this MD Teli Endowment will be dwelled upon by RMIT Madam, who is a faculty from the SVT University, Juhu. Professor Teli has been a source of inspiration for all his students. He has not only influenced the students he has guided, but all the UG students to whom he taught during his tenure in the ICT. Whatever the recognition or the appreciation that the textile department is known for today is exclusively because of his interaction with the outside world and his contacts with the industry. He had also worked for the institute, as mentioned earlier, as the Dean HRD, and also he was the first TKIP coordinator when that program was started. And incidentally, Joshi sir was director at that time. And I don't need to mention about his academic credential, as everyone is aware of his academic brilliance. With these words, I finish my welcome address and request RMIT Madam to share her impressions about Teli sir. Thank you.
As we all know, the noble bond and the sincere belongingness amongst a student and their project guide is a precious one. I would now like to have on stage past PhD student of Professor M.D. Teli and present Head of the Department of Textiles and Fashion Designing Department in SVT College of Home Science, Dr. Armaiti Shukla, to say a few words.
Good evening, everybody. Though we are all familiar with Dr. Teli, it gives me great honor and it's an extreme privilege in introducing a stalwart in the field of textiles and who many of us consider as a role model. Professor Mangesh D. Teli joined Udacity as a young BSc Tech student in 1973. Right at the onset, he had a hat trick up his sleeve. His academic excellence was of being 3 times top ranker at the University of Mumbai, encompassing all branches of chemical technology at BSc Tech, MSc Tech Part 1 and MSc Tech Part 2. He has also been a recipient of many awards since, such as the Sir Vithal Chandravarkar Memorial Scholarship, the Behramji Ratan Lenton Scholarship, Mrs. R.D. Foster Book Prize, and many more. Following which started his journey to associate lectureship in 1989 and a professor thereafter. That is history. The SDGs, or the Sustainable Development Goals of today, have long been an integral part of Professor Teli's brilliant academic career and went hand in hand with his commitment to universal human values, social responsibility, and sustainability. This was evident in his career path of teaching, motivating, and guiding students and faculties at all levels. He has guided over 150 research students and about 35 PhDs. A number of his research students are today faculty of both national and international institutes such as BITRA, Sasmira, Nirmala Niketan, SNDT Women's University, University of Mauritius, as well as ETDI Ethiopia. And we enthusiastically carry his teachings forward. His unique ability to understand the nuances of research from a wide gamut of subjects is exceptional. He has obtained 5 patents, published 350 research papers, including 200 in international journals, presented 100 research papers, edited more than 29 books, 8 chapters, and co-authored a book on sustainable textile processing. His reputation as a renowned orator of international repute is further consolidated as he has delivered more than 40 lectures in research institutions and universities in countries such as USA, UK, Australia, Taiwan, Hong Kong, Thailand, Israel, Switzerland, and many more. He was invited to China 3 times and has lectured at more than 20 universities there, making therefore Udacity, then Udacity and now ICT, a world-renowned institute in the textile manufacturing, processing, and allied fields. His ability to give a fresh perspective to multidisciplinary research projects are evident even before the term multidisciplinary teaching was popular, from joint research novel product development with different departments in ICT such as food, pharmaceutical, dyes, etc. Having served as the head of the Department of Fiber and Textile Processing Technology for more than a decade, he has also served the Institute of Chemical Technology in various other capacities. First is Vice President, Technical Association, Dean, Student Affairs and HRD as well, member of the Board of Management of ICT as a deemed university. He has also served the institute as an acting director or vice chancellor in their absence, and he has been one of the 5 founding members of the society to which the assets of ICT were first transferred to. As a visionary, Professor Teli spearheaded the World Bank-assisted TechWeb Phase 1 program, as Professor Khalid just mentioned, of rupees 33.33 crores. He brought world-class equipment and amenities to all departments of the institution. Placing his faith in the next generation of UICT torchbearers, 11 faculty members were sent abroad in the first year of their training in emerging areas. This TechWeb program, amongst 127 of the national kind, was considered to be one of the best programs, and it also played a pivotal role in taking ICT as a deemed to be university. Professor Teli was also invited by the Ministry of Textiles as a sole evaluator for the Herculean task of India's first flagship program of modernization of the textile industry, That is what we call as TUF, that is Technology Upgraded Fund Scheme, which ranged to 25,000 crores. And he, along with Professor Adivekar and Professor Kale, evaluated more than 5,000 textile units. What is exceptional is that 20 years down the line, these roles are still considered as benchmarks and referred to even by the Textile Commissioner today. He has also played an important role in putting forth a strong claim and making the department the center of excellence in sports textiles. Professor Teli's quite hard work and dedication has been acknowledged by the industry, the government, several institutions and many agencies. I will be missing in my duty if I do not mention at least some of them. Professor Teli was awarded the Honorary Fellowship and Academic Excellence Award by Textile Association of India, Fellowship of Maharashtra Academy of Science, CSIR CNRS France Fellowship Program for Research on Plasma Application, and recently he was cited by the prestigious Elsevier publication Netherlands as one of the top 2% of scientists in the world. Spearheading the move towards strengthening what we always vision as industry-academia interaction, he has been invited as a technical consultant for MNCs like Degussa Hulls USA, Meiji Japan, Huntsman International, Clarion Switzerland, PG USA, and many of the Indian companies such as Century Rayon, Century Textiles, JK Synthetics, Resil, Larsen & Toubro, and many more. Professor Teli has also been on the board of directors of Supertex, Sarex Overseas, and Siaram Silk Mills for more than 12 years. He has been the editor of the Journal of Textile Association for 15 years, and his close association to the governing council members of Textile Association was more than 25 years. With the cooperation of his team of faculties, he has organized several international and national conferences, some which I can mention is Tech Summit over a couple of years, Society of Dyers and Colorists, Textile Association of India, and ITMA. Among them was a prestigious World Textile Conference held under his stewardship in Bangkok, Thailand. And being at the helm of technical affairs, Professor Teli groomed 12 research students and faculties and provided this precious opportunity to many others to present their research papers in an international forum. Besides his academic achievements, true to the spirit of World is One Family, Professor Teli has been a managing trustee of the Lotus Temple, New Delhi. He has been on the advisory board of the Baha'i Academy and instrumental in running graduate and undergraduate certificate programs in education in universal human values, which has been taken up by more than 10 universities such as Shivaji University, YCMOU, etc. He has been ably assisted by his wife and in his free time has conducted over 100 moral education workshops for high school teachers, young parents, officers of the Textile Committee, and many more. We all visualize Dr. Teli as a hardcore scientist at heart. However, other facets of his knowledge and creativity have been hidden. It's only a few minutes back that I confirmed the fact that Sir is an artist at heart too. Professor Teli was appointed by the Vice Chancellor of Mumbai University to design the convocation gowns for the University of Mumbai. As I was closely working with him in the project, we were surprised at Sir's knowledge of traditional textiles and costumes, showing his depth of knowledge and what we as textile community have missed. His sense of color, his sense of design have been completely unexplored by us. His ability to visualize and discuss designs for the occasion helped us tremendously. Throughout his almost 4 decades of long, brilliant academic career, Sir has been motivating force for every student who crossed his path. I'm sure all his students, including me, can testify for his unwavering support. All of us have been fortunate to find Professor Teli present during our numerous milestone-achieving moments. All students under his care became an integral part of the Teli family and were lovingly nurtured academically and emotionally by him and in this context, his better half, Madam Teli. Although Professor Teli, one of the brand ambassadors of Department of Fiber and Textile Processing Technology, Institute of Chemical Technology, formally retired in July 2017, his official connections continued till March 2023 when his final PhD student submitted her dissertation. The journey of guiding the industry and scientists at all levels continues further in his present responsibility as co-chairman of Smart and Intelligent Textiles under DRDO, chairman of Research Advisory Committee of Central Silk Textile and Research Institute, expert committee member of Advertising Standard Council of India. To maintain Professor Teli's legacy of keeping students' interest as top priority, while advocating excellence in all verticals of academia, research, and industry, a few of his former research students of Professor Teli included his first PhD tech student, Dr. N.M. Prasad, and all other well-wishers decided to establish the Dr. Teli Endowment Fund in his name. And the Vice Chancellor, Professor Pandit, delightfully welcomed this move. With their contribution and that of Professor Teli himself, this endowment fund has been established. The interest income of this fund will be used for offering financial assistance to needy and deserving students of ICT. While we are on this platform thanking the donors for the fund, I would like to mention that it is an open endowment fund, and please feel free to support this noble cause as per your convenience, and needless to mention that all these donations for the endowment carries 100% tax exemption. Thank you, sir.
Thank you so much, ma'am, for delivering all these reminiscence and remembrance with your research supervisor. I would now like to invite Honorable Vice Chancellor Professor A.B. Pandit to deliver the welcome address.
Good evening, Professor J.B. Joshi, Professor M.D. Teli, Professor Adirekar, Armaiti, Ravindra Kale, my colleagues, and very nice to see a full hall on Friday evening at 6 p.m. I'm not surprised when you have a speaker like Professor Joshi giving a talk. I'm sure everybody is eager to listen to him on this occasion. So I'm not going to spend too much time, but the topic which he has chosen, we all talk about Vikasit Bharat, and for Bharat to be Vikasit, to be developed, the main constraint for us is the consumption of energy. Professor Joshi will give you and will roll out the statistics for you. But when we grow from a developing country to developed country, that is from current state to Vikasit Bharat, we also don't want to be known as Pradushit Bharat. And that is the key of all, is we do require energy, but we require clean energy without adding to the existing carbon sink which we have created over the past 150 years of industrialization. And Professor Joshi, through his talk, I'm sure will enlighten you, and I think the last part of his title, the option of nuclear energy, really worth looking into, because we should embark on activities which we have resources for. No point in embarking on activities where the resources also needs to be imported, and that we cannot result us into a Vikasit Bharat. So I would like to welcome all of you on this occasion of second Professor M.D. Teli Endowment Lecture, and along with you, I also eagerly look forward to listening to Professor J.B. Joshi, and I welcome you on behalf of ICT and all my colleagues to enjoy today's deliberations. Thank you.
Thank you so much, sir. I would now request Dr. Kedar Kulkarni to introduce our speaker of the evening, esteemed Chancellor Padma Bhushan, Professor J.B. Joshi.
Good evening. It's a real honor and pleasure to introduce today's speaker, Padma Bhushan Honorable Chancellor Emeritus Professor J.B. Joshi sir, who is an outstanding chemical engineering professional who has developed novel processes, designs, products and implemented in large, medium and small scale industries, including designs of more than 1,000 reactors for commercial operations. He has developed efficient designs of cookers and stoves and held more than 300 workshops for promoting science awareness among school-going students. As a president of Marathi Vignan Parishad, he is actively driving the task of improving the scientific temper of the society through different activities. Professor Joshi has done truly outstanding work in the areas of multi-phase reactors, which has been widely acclaimed. He has succeeded admirably in developing design procedures for multi-phase sparged and mechanically agitated reactors, which form heart of the chemical process industry. He was the director of ICT from 1999 to 2009. He has a research and teaching experience of 51 years. Some of his research areas include fluid mechanics, multi-phase reactor designs, computational fluid dynamics, atomic energy, solar energy, bioenergy. Professor Joshi has guided 113 PhD and 61 master's theses and also 25 postdoctoral fellows. He has published more than 500 papers in various international cited journals and more than 60 state-of-art reviews, monographs and book chapters. He has now reached a hallmark figure of 30,000 citations with an H index of 86. He has been honored with numerous prestigious national and international awards, among which he was crowned with the honorary title of Padma Bhushan by the President of India in 2014. Presently, he is holding the position of Chancellor in our institute. Thank you very much, and please, Doctor.
Thank you so much, sir. As we all are aware of the scenario of climate change and its prime significance is almost in all the elemental existence in the entire world. Considering the ongoing concern over it basing upon several such parameters, it becomes crucial for everyone to think in terms of clean options to save energy and utilize the available energy efficiently. To talk more in depth, I would now request today's speaker, Padma Bhushan Professor J.B. Joshi sir, to take over the dais for the lecture and request all the dignitaries on the dais to occupy their seats in the front row of the auditorium.
Honorable Vice Chancellor, Professor M.D. Pandit, Professor M.D. Teli, Mrs. Teli, distinguished delegates on the dais, off the dais, and my dear students. This hall is not new for me. First time I came here was 57 years ago, and I must have given hundreds and thousands of lectures, but not from the stage, from this location. I hope all of you are able to see me. Yeah, thank you. Thank you. As was introduced Professor M.D. Teli, I was director then, and his contributions have been really immense. The proposal to be made to the World Bank, and we received 33 crores, the way in which he wrote the proposal and presented, above all he made friends, the government friends, the World Bank friends, and at the end our project was selected as #1 project in the. So I must have thanked him at that time, but I thank him 15 years later for his job. Professor Shukla of Textile Department, he also helped the institution. Professor Ravi Adayurekar is helping, And Dr. Kale has shown all the indications of commitment to the institution. Therefore, many times I feel if one wants to learn sincerity, commitment and devotion to the institute, one should go to the Department of Textile and Fiber Processing Technology. I will talk about climate change and what are the different possibilities to abate the effects of climate change. Next slide. This year, several news items have come in different newspapers. For example, Indian Express says, Mumbai witnesses highest rise in sea level among 15 Indian cities to continue rising until end of the century. That is Indian Express. The Times of India. Global warming, 4 districts of India go below sea level. Then again Indian Express, the sea level submerged 16 villages, and so on. So many news items are there. Next slide. It is said that the global warming is the result of liberation of greenhouse gases. And greenhouse gases are carbon dioxide, methane, nitrogen oxides, and fluorinated gases. These are the major components. What happens really, a layer is formed of these gases, and this layer is transparent to the sunlight. They reach the earth. The equilibrium temperature of earth is about 30 degrees centigrade, and it also emits energy. And it is a high wavelength energy, and all these greenhouse gases, they prevent all these greenhouse gases from going out. And therefore the energy associated with the emitted energy remains inside this loop, and therefore the warming occurs. So energy definitely comes from the sun. It reaches earth, earth emits, and it is prevented somewhere. And that prevention is mainly by these gases. So from Industrial Revolution, that is 1750, at that time carbon dioxide in air was 280 ppm. And in 2000, and particularly now, it has become almost twice. Similarly, this is in parts per million, if we calculate in gigatons, it used to be 260 gigatons, which has become 350 gigatons. What is the contribution? Combined heating imbalance is because of 66% is by carbon dioxide, about 16% by methane, then 7.6%. This particular point, that various sources of carbon dioxide, various sources of methane, and their percentages, I'll repeat again and again, and I'm going to present all the data. You kindly look at the message rather than the data. Data will support the statements. Next slide. Professor Sukuro Manabe, a Japanese atmospheric physicist, Nobel Prize for 2021. And he developed a simple mathematical model for which he got the Nobel Prize. He says the temperature at the surface of the earth falls down by 2.28 degrees when the level of carbon dioxide was made half. That is, right now it is about 400 ppm. If it is made 200 ppm, then surface of the temperature will reduce by 2.8. If it is done other way around, if carbon dioxide is doubled, then it will increase by 2.36. But if average temperature right now is 30, it will be 30 minus 3.26. And if it is double, then it will be plus 3.26. And for this particular conclusion, he was awarded Nobel. Next slide. So major source of carbon dioxide is fossil fuels and industrial processes. More than 65% of our energy, electrical energy, comes from thermal power plants. Where in thermal power plants we burn coal or oil or gas, and lot of CO2 is generated. All that CO2 is the major source. Plus all the industries, all of us are closely related to chemical industry, and majority, more than 95% industries will have a boiler as a component. Whether it is dyes or textiles or food, it really doesn't matter. And there we do the same activity of generating steam as a major utility, and carbon dioxide is liberated. Methane, the NOx comes from fertilizer plants. That is, the major chemical fertilizers are NPK. And while making N, that is sodium nitrate, lot of NOx gases are liberated and they go to the atmosphere. The principal problem there is the solubility of NO in water is very limited, and therefore any absorption column, the size of which we can imagine, maybe 5 kilometers, right? Then also bringing down CO2 from say 200 ppm to the desired level of less than 20 ppm is difficult. So all that NOx goes to. There are now new technologies in which I am also involved, and it can be made more and more economical. But right now at least the NOx from fertilizer and the biomass. The biomass has nitrogen, and when that biomass is burnt, then we get nitrogen oxides. Methane also comes from biomass and waste. That is, waste, when it starts operating under anaerobic conditions, then methane is generated. And methane is also generated from the rice fields. Wherever good quantity of water is required for that crop, the methane is generated. So methane source is there. And fluorinated gases, we know wherever chilling is required, the fluorinated. And some of the drugs are also fluorine based, and this is this. So the point up till now I have told you is why the global warming occurs. It is mainly because the energy which is received by Earth is definitely permeable through these greenhouses, and it becomes an insulation. So all that energy remains inside, and if you take energy balance, the Earth warms up by mCp delta T, and that delta T we call as global warming. And that thick layer is of carbon dioxide, methane, NOx, and fluorine compounds. Only this much I have told up till now. Next slide. So if you see CO2 emissions in billion tons, it used to be approximately 3 billion tons, and then went up to approximately 400 parts per billion. If you see nation-wise, the China produces maximum, then comes United States, So we are third largest emitting nation in the world, then Russia, then Brazil, then South Africa, then United Kingdom. So this is why I have done this is mainly because later on I want to tell you what are the possibilities, what are the possible technologies to abate this particular phenomena. Next slide. I already said India is the third largest emitter of carbon, right? And this much was carbon dioxide in 100% earlier, 58%, and over the years is approximately 2018 now, is now more than 64%. Then these are other gases. We need not go into the details of these numbers, but then methane and then NOx and then fluorinated gas, how they have increased in numbers. Next slide. I think let us read this slide little patiently. If carbon dioxide concentration is less than 1000, there are very limited health effects. If it is between 1000 and 2500, we get a fatigue, loss of focus and concentration, uncomfortable stuffy feeling in the air. If it is between 2500 and 5000, we get headache, drowsiness and tiredness. It is between 5000 and 40,000. Why I am telling you majorly is I come from the village, and those who use biomass-based cook stoves, they face these kinds of concentrations. Violates OSHA requirements, severe headaches, slight intoxication, depending upon exposure time. If it is 40,000 to 100,000, then immediately dangerous to life or health. Dizziness, increased heart rate, sweating, difficulty breathing, seizures, loss of consciousness, and above 100,000, loss of consciousness within few minutes, coma and risk of death. This is what are the effects of carbon dioxide. Next slide. Why we should limit below 2 degrees centigrade warming? Now it is warming up, and the recent newspapers say that we have already warmed up by 1.5 degrees. And we should not go beyond 2 degrees. Where from this number has come? There was a German group of scientists endorsed by, among others, a council of German scientists advising Angela Merkel, who later on became chancellor, the nation's environmental minister at that time. Their thinking was human civilization had developed in a period when sea levels remained stable and agriculture could flourish. Staying within that bound and preventing global average temperatures from more rising than 2 degrees seemed like unreasonable. So this was a report of a committee. The critics grumbled. What they said was this is an arbitrary decision. But scientists could produce evidence that above 2 degrees centigrade, rapid sea level rise, which has now started, risk of crop failure, collapse of coral reefs, all this will happen. And by 2009, nearly every government of the world has endorsed 2 degrees centigrade limit. Next slide. So, India is not there. Our bottommost is there. Are you able to see backside? So we are polluting 1x, UK 4x, China 4x, France, Norway 13x, Ireland 22x. We should not be happy about it. We should also curb. Our number is 1 mainly because of it is per capita number. And our population is 1.42 billion. Next slide. The GDP is expected to grow 1922 about $2,500, and in next 2-3 years up to $3,000 per person per year. And total primary energy consumption, I want to emphasize here, stress upon, as the population rises, as the human activity rises, the consumption of power is directly proportional to the population on the earth. And per capita US dollars, here you see our per capita income was maybe $20, which has now risen up close to 2,500. And this is the primary energy consumption, terawatt hours per year. We are somewhere here, and we expect that there shall be 7.6% growth rate, and we would like to be equivalent to the developed nation. Then the GDP and the emissions of carbon dioxide will go up to this point. Next slide. So what do we mean by net zero? The all greenhouse gases, the names I told you. We should do something in this box or in this glass in such a way that the atmosphere is cleaned. Particularly, we need to develop carbon sinks. So net zero is a climate outcome where any greenhouse gas emissions through man-made sources are countered by removing such gases in equal amount. It's simple, straightforward to understand. Next slide. Usually all the nations, they meet either once in 3 years or once a year. And just now, one meeting had happened in, I think, Czechoslovakia. And there, all the nations, they agree upon this is our present emission. Now our ongoing emissions we will curtail, and whatever greenhouses have been collected in the atmosphere, we will reduce. So we give promise to the world that we shall do like this. But we give promise to, in the Paris Agreement there are promises, and here also there are promises. Both are equivalent. I'll read only one. What India has promised to the world in terms of present greenhouse gases, and is our commitment of our institutions, of our population, of our government, to reduce the emission intensity of GDP by 33 to 35%. So whatever emissions are there per GDP, we shall reduce by. If population grows, that is not considered. It is per GDP. By 2030, we will do that. Then 40% of fossil fuel power generation capacity will be achieved, fossil-free power generation capacity by 2030. So in another 6 years, whatever coal-based or oil-based or gas-based power plants, some of them are retiring, anyway retiring. But the fuel used for these power plants will not be fossil fuel, and we will have 40% reduction. Creation of additional carbon sink by 2.5 to 3 billion tons of CO2 equivalent. So these billion tons, we have a very interesting piece of information. We have 18 crore cook stoves in villages. 28% of the energy, whatever is used in India, is used for household cooking. Right? Whatever is pollution generated by cook stoves, 15 lakh women and young children, they die. I told you the effect of CO2 concentration and the like. Most importantly, if we improve the efficiency of cook stove from 12-13% to 40%, and it is always possible to increase it further, we have realized 58%. So when we do that, then out of these 3 gigatons, we can reduce by 1 gigaton, just one activity. Develop new designs of cook stoves and try to see that the entire population uses these new cook stoves which are pollution free. So 2.5 to 3 billion tons. So this is our promise to the world. We shall do that. I told 1 billion ton through only cook stove and 40% fossil free. That may be either solar or nuclear, and I'll come to that point a little later. Next slide. So these are actually it is the same thing, but words are different. Maybe I may not read it. We have that to the greenhouse gases, quantitatively and qualitatively, whatever we are generating, we will keep on reducing as we move on through the years, and whatever has been accumulated, that also we will reduce, and how much we will reduce, these numbers are given in our promises. Next slide. What is the energy demand for a near future in India? Whatever I have told up till now is there are greenhouse gases and why they enhance the temperature of the earth, and enhanced temperature of the earth results into many more drastic changes in the atmosphere. Under these conditions, how we should move forward then? We are already polluting, our per capita income is to $1,250, which we wish to make it $11,000-12,000, maybe approximately 7-8% growth rate of economy over next 8-10 years, so that it will become 12,000 equivalent to developed nation. But while increasing it from $1,250 or $2,000 per person per year to $12,000 per person per year, while increasing this will happen, as I told you and emphasized also, the per capita income is directly proportional to energy consumption. And we want to increase our per capita income almost 5 to 6 times. Then we will pollute 5 times. We have already polluted, so that is to be reduced, and the further growth rate 5 times, we should plan in such a way that we curb the release of greenhouse gases. There will be much higher energy demand in the manufacturing sector, which is expected to rise by 30%. Here some reasons are given, that is, we wish to increase our per capita income, then what will happen? The summary of this slide is our emissions shall increase with respect to time. Next slide. So if we have only 4% growth, then million tons of oil equivalent that our nation will release is 200. If our economy progresses by 6%, then these will be the emissions. We are expecting 7.5%, then we will be releasing approximately 700 million tons of greenhouse gases. So how do we carry out the development, further development? Next slide. So growth in installed captive capacity, usually the energy required for steel industry the cement industry and many of the chemical industries, those who have boilers, they have captive consumption, particularly in sugar mills. High temperature steam is generated 25, 30, 35 atmosphere. Electricity is generated and remaining pressure is sufficient for carrying out entire the operations of sugar mill. So these are called captive. The energies are generated there and consumed right there. So that itself will enhance from 39,000 to about 78,000 in 8 years. So we have already done that. Next slide. Other energy requirements. The energy will require for water. In 1951, the population was 361 million, that is 36 crores, and we needed this much water. And now by 2050, it will be 164 crores, and we will need this water. And we can get this water only from sea and by supplying energy. If we want to use membrane process or any other process, then we need to utilize energy. Next slide. Impact of the carbon tax in European Union. What is going to happen? Carbon border adjustment mechanism to impact between 15% to 40% India's annual steel exports. What it says, that if carbon tax comes into existence, all our exports, they will get affected. By how much? By 40%. CBAM compliance could pull down the profits of Indian steel exports by 60 to 165 million tons between 2026 and so carbon tax is coming, and if you don't do the job, we have to pay. We have to pay for the job that we are doing. Next slide. Global estimates of technical potential of renewable energy. This is global. So solar, it used to be 40,000 million oil equivalent up till now, and there is this much scope available. For wind, this much scope is available. Geothermal, this much scope is available. The hydropower, which is shown here, the scale has been enhanced, and from ocean we can get. So these are the possibilities to get energy without the release of greenhouse gases. Next slide. How much we are getting now? In this slide, I am going to emphasize that if we practice all the available mechanisms for generating energy, the total is not coming out. See, there is one possibility that we will not develop. Whatever is the present energy consumption per person per year, we will have same thing in 2030, 2040, 2050. But population will increase, right? The second case is we really develop by 6%, 7%, and by 2050 we become something like Western country and make per capita income 12,000. Then under those conditions, what are the energy possibilities? If we implement the entire area available for solar energy and all the possibilities of wind energy and whatever renewable is there, ocean, etc., all of them we add up, and the need then what is the difference? And the most important point of this lecture is what do we do about that difference? We need something because of population growth and because of the development that we want, and we employ all the resources, you will get something and there will be huge difference. Now I will explain the slide. That is the solar, you implement everything and you will get 2000 terawatt hours. These are estimates of different agencies, but the overall prediction is this much. 100-meter height of the wind we increase, and then also we will get 978 terawatt hours. Hydro, we put all in India on Ganga, Brahmaputra, everywhere we wish to have. Wherever energy is available and we can economically implement, total will get 3,826. But what we need is 10,000. And all this implemented is just 4,000. So extra 6,000 terawatt hours per annum, where from we want to get? So there is a compulsion now to do something. There is no option, absolutely no option. So therefore, next slide. Therefore, the next slide says that what is the responsibility of different nations that they should abide by. And for United States, they are releasing 470 grams of carbon dioxide per unit of electricity right now. And they should reduce the CO2 emissions by 18%. I'm sorry. This is their nuclear component in the energy mix, and they should reduce by 11 grams of CO2 from 470. China is 680, 2.2% is nuclear, they should reduce by 24. And there is a study by MIT in USA, and they have modeled for next 500 years. They say that not 11, you go to 1 unit of gram of carbon dioxide per unit of electricity. So the recommendation is irrespective of the nation. And India 815, and we have only 3% nuclear. So you must have got the sense from me, from this slide, that we still want 4,000 terawatt hours to 6,000. There are no options. And if you want to produce, then what is the carbon dioxide that we can emit to the atmosphere? Next slide. So for qualifying energy systems, the coal is producing this much, and we should have something which produces only 12 grams or 11 grams. So the first option, which is permissible, is nuclear. All others show greater than, show me the previous slide. So how much? Only 11 grams US should emit for 1 unit of electricity. China should reduce by 24 grams. But MIT says 1 gram. So in view of this, next slide. In view of this, if you want to go to 1 or 11, at least the possibility starts from here. And first is nuclear, then wind offshore and wind onshore. But wind offshore and wind onshore together, we have very huge coastal line. And if we implement everywhere, then also it is not going to give more than 10% of what we need. Next slide. So I have made an introduction for the need of nuclear energy. We want something. By doing something, we can go only up to this stage, and for the balance, whatever we wish to say, don't wish to say, there is a compulsion that we shall use nuclear energy. Next slide. So, if we install a plant of 100 megawatt, how much different energy sources are efficient? Normally, we should get, if our plant works all 24 hours and 365 days, then it should give 2400. But because of some difficulties in operation, nuclear power gives 2100, more than 90%. coal gives 1500, natural gas gives 1020, hydroelectric gives only 955, because there are some days in the year where water supply is not available. Concentrating solar cooker, solar energy will give 792. So the point I am emphasizing is there will be certain cost of installation of nuclear. Right? If it is coal-based, it is 10 crores per megawatt. If it is gas-based, 8 crores per megawatt. If it is solar thermal, 20 crores per megawatt. But that is giving only 25% utilization. We have a daytime not more than 6 hours. And we install a plant in 12 crores, so eventually the real cost of investment is 48 crores. But nuclear gives the maximum efficiency. Once we put it, we can comfortably say that it will be more than 90% efficient. Next slide. How much is the nuclear potential? I will simplify this slide, it looks rather difficult. We have uranium reservoirs. Which are approximately of 800 tons per year of natural uranium. So in phase 1, we shall use only those 800 tons, and because of the agreement of 1, 2, 3, we are permitted to buy natural uranium from other countries. So using natural uranium and using the fusion energy, generate the steam and use the steam in the turbine to produce electricity, that is phase 1. Right? This fuel, when it is completely burnt, the natural uranium 238 gets converted to plutonium. Right? I'm telling you a 3-stage program. The plutonium, as compared to natural uranium, the fission rate is 100 times. And therefore, these are called fast breeder reactors. Right? These fast breeder reactors will be our development in stage 2. And when plutonium burns, it generates high quality uranium. We separate. So we need technologies for the separation when stage 1 is over. When stage 2 is over, then concentrated uranium or high quality uranium we will get. And that high quality uranium plus thorium is stage 3. The point which is important in this 3-stage program is thorium that we have and uranium coming from stage 2, we have for next 500 years, 1000 years, there is no problem. Right? As far as source is concerned. Next slide. What I wanted to tell you, that we learn here chemical engineering and chemical technology. I'm drifting a little bit. And in my introduction, it was said that I work in atomic energy, I work in bioenergy, I work in solar energy, all kinds of energies. And then I have designed more than thousands of reactors, implemented, and the cash flow generated is more than 40,000 crores per year. But I'll tell you the secret. Every one of you will generate 40,000 crores per year. See, the chemical engineering for design any reactor and chemical engineering required for atomic power plant or chemical engineering required for biomass cook stoves or getting crude oil from biomass or bamboo, for example. Chemical engineering is exactly the same. You have thermodynamics, principles of thermodynamics. You have chemical reaction engineering. Whenever reactions are there are rate processes. There is a mass transfer rate, there is a heat transfer rate, there is a momentum transfer rate. And above all, we engineers learn economics. Right? I have been teaching here and will continue to teach. What I tell my students, that while doing your profession or while implementing the energy system, you will get variety of suggestions. You'll get variety of suggestions. As soon as anybody gives suggestion, you should have an embedded chip inside. Evaluate whether payout period is 4 or 5 years or 3 years. What is the IRR? What is the investment? Do I have investment? If that idea is very good, praise that fellow profusely. That is so good, so nice. I did not hear like this in my life before. Praise. But if our IRR is not attractive, payout period is 10 years, 20 years, then just give a nice smile. So it is our duty now, without smile, we need to generate technology. After generating technology, you will get wealth, you will get praise, and then your smile is a different aspect. I will tell you a case, little different from there was a problem in one Indian industry making hydrogen peroxide, right? And in hydrogen peroxide, a certain molecule, ethyl naphthalene, is hydrolyzed. If it is over-hydrolyzed, over-hydrogenated, then we get C. Let us say A going to B going to C, and B is the desired product. The reactor is a vertical cylindrical vessel in which we have a catalyst, and hydrogen we pass from the bottom, and hydrogen flows in the form of bubbles, right? Now the bubbles generate turbulence, and because of the turbulence the catalyst gets suspended. And we call this mechanism as suspension because of dispersion. And suspension because of dispersion is always exponentially decaying. You get very high concentration here and very low concentration here. If you want to increase the dispersion, you need to increase the gas flow rate. Right? When we studied this mechanism, it said that if hydrogen concentration is high in the fluid phase, then we will get C. If it is close to zero, then you will not get C, you will get B only. This is the mechanism which said. So what was required? The rate of dissolution of hydrogen shall be less than the rate of chemical reaction. Right? If we increase the gas, rate of dissolution increased and quantity of C increased, and when we were assigned the problem, only 70% per pass conversion and 70% selectivity. Only that, but a big problem. And if solved by increasing gas flow rate, it becomes worse. So therefore what was done, and this is the basic point I emphasize all of you for designing new nuclear reactors. I'm telling you the story of hydrogen peroxide. Next slide. What we did was connected a pipe in parallel to the main reactor. Right? And it is easy to see here that this main column has hydrogen bubbles, and here we separate gas and liquid, and only liquid and catalyst comes down. Now since the density of gas is negligible, the overall average density of gas liquid solid is less than the density on this side. So the static pressure energy here, which is rho gh, and it is rho gh here also, and rho is more here than rho here, static pressure at the bottom here is less than the static pressure here. And there is a pressure difference, and therefore flow starts occurring, and it goes upward, and we call it riser, and it goes down in the downcomer. Particles were being suspended by dispersion. Now when upward liquid velocity is equal to particle settling velocity, all the particles will remain suspended on their own. And the job of gas phase for suspending the particles was taken out from the gas and given to the liquid, and now the catalyst concentration was also uniform, because a flow of liquid and downflow of solids is satisfied everywhere in the reactor. So the conversion increased from 70%, 80%, 90%, 100%. Selectivity increased from 70%, 80%, 90%, 100%. If my another 50 lectures are kept, every time I will tell you one success story, which is equivalent to 40,000 crores. So we call this as natural circulation. There is no pump. We have created deliberately a density difference. Deliberately density difference at these two locations, and therefore flow has started. If the downward flow, it is normally difficult to understand. Here the density is the average density into rho gh. Most of the column is occupied by liquid here. But if we introduce gas at this location, the overall density of this limb can be kept still higher than this point, and circulation will continue. And if gas introduced, the bubbles have a velocity less than circulation velocity, we can introduce bubbles and get this advantage. There is one American company, those who offer carbon monoxide to methanol, ethanol, or carbon dioxide to methanol, ethanol, or methane to methanol, so all these technologies. And they do it by gas phase fermentation. See how we keep objectives while designing any plant. They surveyed the entire world who is capable of doing this, and because of some reason it came to me. The statement defined was, if we make 100 tons per day methanol, the capital cost should not be more than $20,000 per ton. And the entire operating cost, everything put together, shall not be more than 14 cents. Solubility of methane is very low, and it required that the rate of dissolution of methane shall be 5 times than the known, whatever are the known equipment in the world. But this is unless we do this, then it is not going to be economical. Therefore, I use this idea. First of all, I use this for hydrogen peroxide. Then I introduce gas at the bottom. The details are in my patent. You can read the patent. But it resulted into micro bubbles of 5 microns, 10 microns. There was a mechanism provided at the inlet, and the bubbles got preserved because of the fermentation and the proteins produced. And we got dissolution rate 4 or 5 times, and the plants, such a plant of very high, this is a fermenter now. The largest capacity fermenter is now in China. It is operating, it is working. So I'm carrying out large number of workshops why we should fear China. can we introspect ourselves while designing the plant? Do we have sufficient attention to the capital cost? And then we face the difficult times of the goods coming from China and ours are not competitive. I think this much diversion, create density difference, create natural flows, and because of that, do something. In the first case, it was mass transfer with chemical reaction. Here also there was mass transfer, but it was a fermentation reaction. This was a chemical reaction. So how this principle, I have been working in nuclear design, reactor design for 15 years. Right? So whatever is my understanding, I'm going to tell you. Next slide. All of us know that 3 accidents have happened in nuclear industry. All of us know. The latest one is in China. I'm sorry, in Japan. Right? And all of them occurred mainly because the pump failed. Right? The circulating pump failed. And circulating pump was used for heat transfer. In heat exchanger, you need to feed cooling water on one side, and the hot fluid that we get from the power plant by fission reaction, that will be on the other side. So once the cooling stops because of the failure of pump, then the temperature inside keeps on rising. And if it goes beyond 1200 centigrade, any metal reacts with local water to produce hydrogen. And air is already there inside the reactor, and hydrogen and air together have created these 3 blasts. Right? So what was required? Elimination of pump. And in this design, there is no pump in the circulation. Just create density difference and create natural circulation in such a way that it is sufficient for the purpose. Right? And now I will show you the exact atomic power plant and where such principles are used. Next slide. It is already there. Now you can show this. This is a core. You show the one bundle, tube bundle. Tube bundle. Tube bundle you show? Is it deleted? Yeah, okay. No problem. The fuel is finally made in the form of tablets. All right? And we take 10 millimeter tube in which we fill those tablets. And the overall diameter of that tube is 10 mm. Now imagine a bigger cylinder in which we put these pipes, 1 centimeter, about 500. Okay? And that cylinder is this cylinder. The core that you see, I hope this is the core in which there are 150 pipes like this, and fission occurs here. Because of the fission, so this is the loop. This is the loop which I showed earlier. Because of the heat supplied by fission reaction, some of the water boils. Right? And the boiled water and water, they go up. And this is a steam drum where steam and water are separated. Steam goes up and only water comes down. So in this loop, there is steam water mixture, whereas in this part, there is only water. And therefore, at this point, the density is less as compared to density here, and natural circulation starts. So there is no pump. There is no pump, that is. So if time permits, I will show you all the natural routes that have been implemented in this reactor design. And these we are recommending for the smaller and micro reactor. So this is one loop. So water goes down because of the fission reaction. water boils, only 10 to 15% water boils, 85% is water. There is a steam drum. The steam goes to the turbine and generates electricity and goes to the utility. Similarly, there are many other, I will just mention what are the loops, I will not explain. I have already explained to you how the natural circulation happens and how that circulation becomes useful either for heat transfer or mass transfer or chemical reaction or whatever we wish to have in chemical engineering. Next slide. So, because of any reason, if the operation goes beyond control, then we need to stop the reactor. Right? And whether a poison, we name it poison, it stops the fusion reactions. Whether that can be introduced into the core in a natural way, that some incidence has happened and now, so there is a water well at the top. Huge water well, 50 meters diameter and 10 meter deep. Can you imagine? Much, much bigger than our swimming tank. And one stream from there, it comes here and opens the valve and all the poison goes to the reactor. When reactor is shut off, the fusion reaction doesn't stop. It continues and there it supplies the energy. So we need to take care of that. So that energy, this black spot, it goes to the well and we have submerged heat exchangers and we should put the heat exchangers in such a way that this is a well but of concrete well and concrete disintegrates at 55 degrees centigrade. So you are condensing steam but making it sure that nowhere the temperature goes beyond 55, particularly near the cement wall. And that is also done by natural. So while I was in atomic energy from 2009 up till now, I have been having opportunity to guide 40 PhD students who have contributed to the modeling, simulation and optimization of each of such loop. Each of such loop. And then, because I'm expert in energy, means expert in chemical engineering basically, I put all these loops together and created an optimum design, which now I call it as a small reactor. Small reactor definition I'll tell you soon. Next slide. So I told you the 3-stage program. In first stage, natural uranium is used. We isolate uranium, plutonium and many other compounds which are the result of fission. And that plutonium is now made in the form of tablets and another pipes, and that is called fast breeder reactor because the fusion rate of reaction is 100 times more than natural uranium. And therefore, the cooling by water has certain thermal conductivity, whereas sodium, liquid sodium has more than 100 times the conductivity than water. Therefore, it is cooled by liquid sodium. I'll quickly explain this, that the sodium is made hot, then it goes to heat exchanger and the water comes in, water boils, the steam part of it runs the turbine, and that is the stage 2. I explained very quickly, but basically there is a natural convection between hot liquid sodium and water, where water evaporates. Again, there is a natural loop. Next slide. Actually, now there is a lot of talk about small and micro reactors in the recent past, how we should be progressing. But in reality, this entire nuclear program started with small and micro reactors. So in 1950, the earlier reactors were 10. and so on, 10, 1500. But now they optimized up to approximately 1000. So we don't want this. Why we don't want this? I will explain to you in greater detail. But now we want these reactors, but much more efficient than what they were at that time. Next slide. About this nuclear power plant design and the separation of the spent fuel, right from 1999, our institution used to have plenty projects. And as a team, we solved. Professor Pandit was there, Professor Patwardhan was there, Dr. Lali was there, Dr. Lal Gaikar was there, then Professor Bhagwat was there. Everywhere participated and solved their problems. The extraction, separation, purification, natural, computational fluid dynamics, everything was done together. So let us look at small nuclear reactors, modular, small modular reactors are small modular reactors having power capacity up to 300 per one reactor. Small, physically fraction of the size of conventional nuclear power plants. Means if you have 1000 and if you have 100, then it is not only 10 times, it is more than 50 times smaller. It is modular. If you want 10, still 1000, they can be put in parallel. And harnessing nuclear fusion energy for converting the thermal energy into electrical energy. Next slide. I'm lost. This is the thank you slide. But I wanted to tell you many more things. Is this thank you slide? Go further. Go previous. So microreactors are up to 10 megawatt. And why microreactors are required? Right in India, there is a huge requirement that ours is a cooperative society and there are 300 families. We want 1 megawatt plant, right? Or there is a shopping place, a mall, a big mall. They want 3 megawatt or 4 megawatt. There is a chemical power plant. Total steam required is equivalent to 3, 4, 5 megawatt. So this is the requirement of micro. But for small reactors are used for safety mainly. And those reasons I'll tell you. So large conventional reactors are 700 plus something, and typically 1000 megawatts. Small are 300 megawatt up to 10, and 10 and below 10, these are called microreactors. Next slide. So I want to show you the natural convection. This is also, very briefly I'll tell you, all the sizes are less. The reactor which I showed you earlier was of 300 megawatt. Now this is less than 100 megawatt and is a small reactor. This is a core where water will become hot, and this is a change in direction. It comes down and it falls back. So we don't need to add water. The hot water goes up and it generates steam. There is a water on the shell side, steam comes out of the shell side, and water, very hot water, more than 300 atmospheres and 350 degrees centigrade, water goes in and returns at 330. And it generates the steam to which it is connected to turbine. It is a small reactor and compact. All heat exchangers, except turbine, everything is inside the reactor. Next slide. So what are the key features of SMRs? Lower initial capital cost. I will read it. If you require, anybody requires, I will transfer my slides to you. Factory-based production. This is very important. Suppose we want to spend 15 crores per megawatt and we want 10 megawatt power plant, then this means 150 crores. You start spending 150 with the present technology. I'm sorry, we cannot make 10 megawatt. Right now we can make only 1,000. So 1,000 into 15, 15,000 you become ready to spend. Minimum 7 to 10 years are required before the plant starts. See the cost of money, and therefore it has become unattractive. Whereas small reactors and small modular reactors, this can be factory fabricated, taken to the location, and it can be assembled. So that period comes down to 2 years. That is the first advantage. Lower initial capital cost, factory-based production, potential for reducing the operating cost further because we are not even using pumps, base load and load following, integration with another. This I want to explain further. That is, whatever is solar energy, in India we get for 6 hours, in US we get for 6 hours, but all those 6 hours are different from each other, right? But energy is wanted. I'm not going to give lecture for another 3 hours. But if I need electricity for further 3 hours, for further 6 hours. So that is continuously required. Whereas solar energy, wind energy, all kinds of hydro energy, I showed you their utilization factor. Nuclear had maximum, whereas it was 20% for nuclear. So this particular idea is known to the world, that is, let there be base power and all this, you can say, temporary fluctuating powers can be added to the grid and then grid can be stabilized. So even if entire India is converted into solar energy and wind energy and hydro energy, all of them are discontinuous. And base energy is required, and base energy and non-polluting is only nuclear energy. Right. Next slide. Continue modular design. Once you do one in the factory itself, we can have parallel fabrication. The smaller size, scalability is there. Passive systems are much more. Actually, the entire reactor is dipped in pool of water. We need not have a well at the top and the reactor separate, but the entire reactor in water. Scalability, passive safety systems, this I explained in detail, that is, generate natural flows to take care of hotspots. Inherent safety, that is what I meant. It is, maybe I can explain a little more. Core damage frequency is very less. If the core melts, then the molten mass goes somewhere. So we have come out with technology where that molten mass melting point and the red mud for aluminum industry has same melting point. So we keep 200 tons of that red mud below the core. If at all accident happens and core melts, it will fall on that, and MCP delta T of core and MCP delta T of red mud, they are balanced in such a way that the cooling occurs right there and no accident happens. Next. So these are the limiting points. End use of SMRs, retrofitting the retired coal plants. So if you want to employ SMRs, the present place right now is the retiring coal plants. So it is retrofitting. So retrofitting the present coal-based power plants by SMR is one challenge. Most of the coal power plants have people living just outside the plant boundary. That is the second limitation. It is difficult to get 1 kilometer exclusion zone in a coal plant. Getting land for other zones, natural growth zone, emerging planning zone, that is not possible. Domestic manufacturing capability has been written as a limitation, But I, as a chancellor of this university, feel that we shall create. We will enthuse our young generation, make them to start up of various components, and this fabrication capability, let us develop, not only in our institution. I am very happy with the young generation. I am confident that they will come forward, and this limitation, as a chancellor, I promise that we will remove it. Possibility to transfer the entire assembly reactor by railroad, this is at the advantage, of course. Next slide. Large number of coal plants are retiring. 1990 some retired, and 2040 these many retired, and they are not getting extension in their life. Next slide. So coal versus nuclear, I have a slide, but I need not explain the coal producing carbon dioxide, and then the active working hours, they are all unfavorable. Next slide. SMR potential to replace retired coal plants. Some of the limitations I told you earlier, the number of acreage required for coal power plant and for nuclear plant, that has been compared. Next slide. Potential of micro reactor now, less than 10 megawatt. Next slide. So 220 pressurized heavy water reactors, we have plenty in India, but these are not considered for small reactors. The safety features are not acceptable. Next slide. For power generation, now we are looking for other options. So if we use supercritical coal, the CO2 liberation becomes less. Supercritical coal plus carbon sequestration, natural gas. So this is the cost of electricity generated per unit, and nuclear is 5.2. Next slide. For chemical industry, if the temperature required is less than 1000, less than 800, less than 500, less than 200, the nuclear power plant becomes easier and easier. So as compared, as required by different units of chemical plants, in chemical industry, if it is steam cracker, 1000 degrees. Steel industry, 1000 degrees. Cement industry, 1400 to 1500 degrees. Chemical industry, between 400 and 500. Paper and pulp industry, 60 to 150 degrees. Textile industry, 170 to 200 degrees. Accordingly, the nuclear power plant become easy and easier. Next slide. The comparison of LCOE, again money. So I explained earlier, where only heat is required and not electricity, then the nuclear power plants, they become even cheaper, because the cost required for converting the thermal energy in the form of steam to electricity, that gets eliminated. Next. So summary is, SMRs are a promising advancement in nuclear technology, and we have developed this technology on our own, offering enhanced safety, cost effectiveness, and scalability. Potential impact is, with their ability to provide low carbon, that is low CO2, reliable power, SMRs could be crucial in meeting global energy demands while addressing climate change. Looking ahead, continued development and regulatory support will be a key to the widespread. We ourselves need more than 1000 SMRs, and the world needs 10 times that. If we develop this capacity in all other chemical industry equipment, we are much, much economical than anywhere in the world. So my last point in my lecture is, let us all together develop this capability and increase the development index or wellness index by a large factor. Thank you so much. I wish Professor Teli and Mrs. Teli a very long and peaceful and with healthy life.
Thank you so much, sir. I hope you all had a great learning session now. We now invite questions from the audience.
Yeah, no questions are there. Yeah, any question is okay.
Why did the government of India stop at only Padma Bhushan? Padma Vibhushan is also there. And I remember distinctly, you directly got a Padma Bhushan, no Padma Shri. So would you have any thoughts into that, please?
I also don't have third standard. I have not passed third standard. From second standard, fourth standard. So if I am taken interview, my interview, where is your certificate of third standard? I don't have. I don't have certificate for master's degree also. Yeah. And about the second, why I am not getting Padma Vibhushan, some things I can do, lecture I can do, but some things others should do, no?
Thank you very much, sir.
No.
Yeah, sure.
One question related to, natural uranium to ultimately the uranium which can be used in the power plants. We have only one facility today in India. So that's going to be the limitations if these SMRs are going to come into picture in the large way. So is there any plan to have more facilities like that, or what's going to happen?
So as I told you, our natural uranium availability is 800 tons per year right now. But now a second site in Andhra Pradesh has been found where we are going to get another 800 tons. Then third is the phosphorus in fertilizer plant. We get phosphorus rock from outside, and which is leached by sulfuric acid to make phosphates.
Yes.
And in the imported rock, there is 100 ppm uranium, natural uranium. When that is extracted, it is more than 800 tons, and therefore that technology has also been developed by our institution to get that. That is 800. And about 5-6 years ago, there was an agreement 1 to 3 which permits us to buy natural uranium from any nation. So part 1, phase 1, no problem.
Okay.
Yeah.
Sir, I have a question. Here, Hemant here. So it's been 1,000 days since Russia-Ukraine war has been happening, and we also have a Gaza-Israel war happening. And recently Russia has also started threatening with respect to advanced stage of nuclear missiles. So nuclear energy is a clean energy, but at the same time, the humans are very selfish, we are all. And because of the war crime, a lot of energies and emissions are happening because of the use. So is there any study done that for 1,000 days so much of missiles are, and what will be the impact on the overall atmosphere, and any kind of a study, and the severities whether known? Because this is something which never was thought in the Paris Agreement. Just a curious question.
Yeah. I'll give you my another book. Actually, I wanted to give a book on the same subject, 5 copies to keep in the library, but I can do it at any other time. We have 3 nuclear accidents, but there is no fatal. No fatal. If dam breaks or we release the water, last year 500 people died. In Brahmaputra, thousands and thousands of people die because of the river Brahmaputra. So people using the atomic weapons, see, there is a culture is one word and development is another word. So if development also includes the cultural development inside, these problems will vanish. What we are looking at is the material development, use of energy, use of materials, and more and more and more. That is creating problems. That is, there is a lot of greed, and greed is resulting into this. So this development does not contain greed, but greed is the origin. But utilization of all these facilities is because of greed. So whether by using Indian philosophy, now onwards we shall develop in a manner of our own culture, that should be the conclusion.
Well said, sir. Thank you.
Hello, sir. Yes, sir.
So
Hello.
one more question related to ultimately when the reactor comes to the end of the life. This is where I again feel what is going to happen when the so many small reactors will come at the end of the life, or where the decontamination also needs to be happen every 4 years or 5 years and 6 years, and so how are we going to tackle
So decontamination, I can, if Vice Chancellor permits, I am ready to give another lecture.
Okay, great.
Sir, usually nuclear power or nuclear power plant face opposition because of its safety related issue and unawareness, or lack of awareness. So I request your comments on these small modular reactors, comparative safety of the conventional power plants, nuclear power plants, and safety of these small modular reactors.
Right. See, the opposition starts because of several reasons, as you know. There is a scientific reason, there is an unscientific reason, there is a social reason, there is compulsive reasons, money coming from somewhere, and because of that there is a reason. As a scientist, am I convinced? Right? When I saw there is no safety problem, means there is no safety problem. And when I have conviction like this, it shall get implemented. Let there be any opposition any time. That is one part. Not only that, the new reactor onwards shall be Indian reactor. And we shall not import any reactor. Last time I announced in my earlier lecture that if nuclear reactor is bought from outside, it will go over my dead body. So we shall develop, with that commitment we shall develop.
Sir, the nuclear energy itself, Professor Joshi has so very well explained to us, and most of us having technological and scientific background, there is no further explanation. As he rightly mentioned, there are even the political reasons wherein many of the countries and the big lobbies don't want India to be self-sufficient. That's also a factor. The one point which Professor J.B. Joshi mentioned, while we are, the so-called the powers of corridor may take definitely and work on this particular plan of Professor Joshi, and here he is committing as a chancellor of this university that we should create that manpower, because at the end of the day, manpower is essential, and the brilliant heads are here in these portals of excellence. So definitely that dream could, come to the fruition under vice chancellorship of Professor Pandit, and he as a chancellor of this institute, it can happen. But while you have this dream, and we all wish good luck for that, but at the same time you made one very important the statistic in fact you gave, and that is about the cooking stoves, and about 14 lakh people almost they lose their life just because of the carbon emission, so much of it. Can we work on that, or can those efficient stoves which emit less of carbon dioxide?
People don't like the same lecturer to continue. Now let us give mic to Professor Pandit, and Or give a lecture on cook stove.
No, I will give lecture some other time.
Yeah.
But just to inform Professor Teli that indeed these stoves are being marketed. The technology has been given to a company which is manufacturing and it is being promoted. But it also requires acceptance, and to convey you the best is this particular stove. We had to go through the trouble to get it BI standards, and it is considered as a 5-star stove, showing the particulate emission as well as the carbon dioxide emission, meeting all the world standards which are currently available for all the stoves. And it is being manufactured and it is being marketed.
So technology is there. Now we need activists to make
To implement it,
to
to
implement
propose it.
yeah.
Thank you very much, sir, for accepting our invitation to the second Professor M.D. Teli Endowment Oration for the year 2024. We are thankful to you for sharing your expertise and knowledge with the audience present over here. Your presence was of prime privilege to all of us. On behalf of this august gathering, I extend my earnest gratitude to you. It was truly enticing for everyone to listen to you on this crucial topic. Now, I would request Professor M.D. Teli to share some thoughts and experiences with us.
Friends, I know it is a little, longer than the expected evening, but the talk of Professor J.B. Joshi on this new subject was so interesting, and everybody was spellbound here. There would be a formal, the vote of thanks, and so I don't intend to say more, except that, first of all, I, thank from the bottom of my heart those students, my past students, and some of the companies who generously donated to this endowment, and because of which we have been able to assist the needy and brilliant students of this ICT. My special thanks are to Professor M.M. Sharma and Professor J.B. Joshi, who actually, they accepted to give this first and second oration respectively under this endowment. And it was really a good start because we got these two eminent personalities speaking to all of you. And I'm sure this is only because of the love, the respect which they, have in their heart for me personally. And I indirectly take it as a testimony for my dedication to this institute. So Professor J.B. Joshi, really I'm indeed grateful to you for accepting the invitation. And, under Professor J.B. Joshi, really it was a fun to work with, because whenever different activities we did, and mainly when the formative age of this ICT getting converted into university, there were so many things were to be done. And when we were working for at an institute level, whenever the certain kind of jobs he would give, he would clearly give the freedom also along with the job responsibility. And he would say that for these 2 or 3 activities, you are the director for that activity. You have to take the final decision. So this is the kind of, the total faith he would repose in us. It would really create a special, the attachment and affection for him. So I am personally grateful to Professor Joshi and also Vice Chancellor Professor Pandit for, accepting to open this particular, endowment, which was in fact initiated by my past students. Thank you very much.
Thank you so much, sir. I would now request our esteemed Chancellor Padma Bhushan Professor J.B. Joshi, sir, to felicitate Mrs. Teli. Requesting our Honorable Chancellor to commend Professor M.D. Teli with a shawl and a Shreefal. Thank you once again, sir, for making it so memorable for all of us. I hope you will also be making your presence next year, the upcoming years, with your valuable experiences and with all the plethora of scientific marbles ahead. I now invite Honorable Vice Chancellor Professor Aniruddha B. Pandit and Professor M.D. Teli to hand over the memento as a token of appreciation to today's speaker, Padma Bhushan Professor J.B. Joshi. Thank you so much, sir. I would now request Dr. Saptarshi Maiti to deliver the vote of thanks.
Respected dignitaries and eminent personalities present in the auditorium, my colleagues, students and friends present here, I thank you all for joining us in this auspicious evening for Professor M.D. Teli Endowment Oration for the year 2024. First of all, I sincerely thank our former head of the department and also former Dean HRD, Professor Mangesh D. Teli, under whose honor this endowment has been started last year. And this year we are organizing the second endowment. Wish you, sir, a very healthy and long life ahead. We are also thankful to Professor Teli's family members, especially our beloved Teli Madam and his daughter Shraddha Ma'am, for their continuous support and active participation to organize this program. We are very happy to have them with us at this August gathering. The program would not have been initiated without their active cooperation and enthusiasm. I take this opportunity to thank the speaker of today's endowment oration, our Honorable Chancellor Padma Bhushan Professor J.B. Joshi, delivering an excellent lecture on the topic climate change, clean energy transition, energy options, and relevance of nuclear power. In his speech today, he has rightly pointed out the growing concerns on climate changes in today's world and its adverse effects on the environment. He clearly and lucidly explained the relevance of energy conservation and utilizing the available sources of energy, especially focusing on the importance of nuclear power. He has also enlightened on the scope of alternate renewable sources of energy in today's competitive era. Thank you, sir, for your expert and fabulous talk on this theme. I am grateful to our Honorable Vice Chancellor, Professor A.B. Pandit, for his gracious presence among us. I would also like to thank our Registrar, Professor B.F. Jogi, his invaluable support to conduct any event at ICT is commendable. I take this opportunity to thank our head of the department, Professor Ravindra D. Kale, for his enthusiasm, tireless effort and encouragement to his colleagues to conduct any program in our department. And needless to mention, I sincerely thank our Dean HR, Professor Ravindra V. Adivarakar, and Dr. N.M. Prasad, founder and director of Chemistar Intermediates Private Limited, dedicatedly taking the initiative to create this endowment and starting the series of annual lectures under this endowment. The result of such tireless endeavors has led us today to successfully organize the second oration under Professor M.D. Teli Endowment. And last but not the least, I honestly thank the audience for their positive and enthusiastic presence throughout the program. Without your presence, no program can be successful. Thank you all. Stay safe and blessed. Thank you.
Thank you, sir. I'm immensely thankful to all the students, faculty and the industry personnel present over here for their active participation in today's event. We have been fortunate enough to be backed by such a team, having so great versed in their job and putting every single effort which would have not made this event such successful. Now I request all to stand at their respective places for the Rashtra Geet.
सुजलां सुफला मलयज शीतला सस्यश्यामलां मातरं वन्दे मातरम् शुभ्रज्योत्स्ना पुलकितयामिनी पुल्लकुसुमित द्रुमदलशोभिनी सुहासिनी सुमधुरभाषिणी सुखदां वरदां मातरं वन्दे मातरम् वन्दे मातरम्.
Thank you all. I request you all to now proceed for the high tea arranged in the first floor above the marble hall. I request all the dignitaries to gather at the dais for a group photograph. Students are requested to stay back and kindly proceed after some time once the dignitaries move ahead for the refreshments. Thank you so much.